Thank you for the introduction and thanks for inviting me for giving this webinar presentation. As already mentioned in the title, I will today talk about simulation and multiphysics simulations. So there are different physical domains which interact with each other, and we will talk about this and specific topic of power electronics. Maybe before I start, I can introduce our company. The name, it's a family-owned company since the mid-80s. CAD-FEM means CAD, CAD geometries, and FEM stands for finite element method. So you understand our company is dealing with CAD, with simulations, numeric simulations, and finite element method. We are very focused in a German-speaking area in the middle of Europe. So Germany, Switzerland, Austria, with several locations, with offices. We're working mainly with ANSYS products together, but we use also other software for the simulations. We help companies to start with simulations. We do consulting. We do projects together with our customers to implement automatization, software automatization, and so on. I think our strong focus is also on the engineering experts. We are more than 130 engineering experts, simulation experts, so we can provide support, we can help to you with simulations, and that's also our motivation. So simulation is more than software. It's not only that you have the software and then you can start. We also give seminars, trainings. We have more than 130 different seminars in our program. We have e-learnings, we have online trainings, and so on. And we're working very close with our customers together. We are not only in Europe, we have also more widely around the world. So there's also a strong focus in the India Southeast area, where we have a partner company, and also in East Europe, where we're working close together with other channel partners and companies there. So we're working nearly worldwide and bundling our competence together. But I think that's enough to our company. I want to start with the topic today. So the topic today is multiphysics simulations, specific on power electronics. I want to explain this on a simple case or on an example, which we did for testing, which we did with one of our partners together. So you see on the right top here, something called quantum well laser diode. It's an electronic component. It's maybe not known, or it's not the typical high power or power electronics application. But in this small component, there can be very high power. There can be very high currents. They are not running continuously. They are switched on and switched off to create these laser pulses. And the general question is, okay, how much power I can put in without getting hot, or maybe I have to think about cooling. So that's the idea. How I have to design the cooling, how I have to design the whole system that I can create high power for the application, for the runtime. Not only once, is it working once, it should work in an operation condition. It's maybe built in a car, in a system for laser radar systems or something. So it should work for the whole driving process. And I want to simulate this one. Okay, so what I have as an input, when we're talking about simulations in general, if you're talking about field simulations, I come to this later, what I mean with this one. We need geometry, we need material data. So we're really interested, or we need to know the geometry, how it's connected, everything, how is the surrounding. And we have the input, which is, for example, the signal. Yeah, we know that there's pulses, there's higher pulses, lower pulses, depending on the situation, what we want to do. That can vary. They can come continuously, they can come in different time steps, and so on. So what we have is the typical signal. We have our component, and it's an electromagnetic component. So if a current is flowing, we have get Joule heating, losses are created. But also if we're switching on and off, that's some dynamic process where we see, for example, eddy effects. So there could be current losses, heat generated on parts which are not directly in the current flow, which are not direct in the path, but somewhere around, and they're producing also losses or currents voltages which charged up and so on. But the general what we are interested in is the losses. So if I do a simulations, I can get out such a picture, for example. That's always nice to see, a lot of colors, but on the left side you see the scale, so that's maybe the more physical part which I'm interested. I want to see, okay, what's the maximum power? And with the colors connected, where's the maximum power? And the first thing which we see is the losses, the ohmic losses, the Joule heating, or what we get in this one can be also magnetization losses. They're not evenly contributed. There are parts with higher losses and parts with lower losses. But that's something which I can simulate. I can get it out depending on the signals which are put in. You see here something, an arrow which says temperature. It's sure if this system is working at room temperature, there will be different losses than when it works at 100 degrees Celsius, because the conductivity and magnetic properties and so on, it depends on temperature. So that means we need a multiphysics workflow, especially electromagnetic. That's something which is really close. There's a huge influence on temperature. And so that's why I need also some simulations or some knowledge about the thermal behavior. The thermal behavior depends mainly on the loss distribution. So we have already seen the losses are not everywhere the same. They are locally distributed. And on the boundaries, means is it cooled by airflow? Is it in a fixed box and there's no airflow? Is there some other components around with high temperatures and so on? So that's mainly influenced the thermal simulation. So one of my inputs, as I said already, are the losses. But there can be also other thermal loads. For example, I removed the semiconductor part, the laser part, which you see the green parts in here, because that's not really the electrical part, which current flow makes the losses. There are other loss distribution. These thermal loads, these losses in the semiconductor part, in the laser part, can be as an input from data sheets or can be simulated in another way, can be measured, whatever. So I have one part is the losses, one are thermal loads, could be also outside loads, and my thermal boundary conditions. So that can be, again, a function over time. So I haven't mentioned this. On this axis, we have seen the time. On this, we have seen the current. Here we see the power over time. So it's a transient behavior. As I said at the beginning, we want to know how it behaves over a certain time. And when I apply the currents for a certain range over a time. And there could be boundary conditions, as I said before, surrounding temperature, heat transfer coefficients, and so on. That goes already very detailed into the thermal simulations, but that's other input parameters. And what I want to get out is the temperature. Again, I got a very nice colored picture of the temperature distribution. And again, most important, or the next step to look into, is the scale, what I'm seeing here. And if you look a little bit closer, you see the temperature range is not a big difference. So even we have here a huge difference in ohmic losses. There's several scales. Here the temperature is very contributed everywhere the same. There's 1 degree difference. Yeah, that's because of the materials have a very good thermal conductivity. And what we see is that the steady state case. So if I'm running with this one at some time, you get a steady state temperature. And it's not distributed this much. But anyway, with this input, I have to go back, because I mentioned temperature has a huge influence on the electromagnetic properties, or can have a huge influence. So I have to put back this information on the temperatures for the electromagnetic simulations. A second part is, if I have temperature, I get thermal stress. If it's not made of all the same material or same materials which have the same thermal expansions, so I'm introducing some stress in the system. So mechanical loads can be additional if it's someone is hitting it, or if there's a movement, rotation, shaking, whatever. It could be additional mechanical loads. So one input is temperature, other could be mechanical loads, and it's also important how is it mounted, where's the fixing point of the system. I can make a structural simulations, and finally I get information about the stress level, about deformation in the system, and so on. So that's a typical multiphysics workflow, starting from the electromagnetic side, thermal and structure. This can be expanded also that we have other parts which have an influence, but I would say that that's the main workflow when you have electromagnetic thermal structural simulations. Maybe you see also there's something missing. So if I get the stress, the mechanical deformation, I don't feed this back to the thermal simulation, electromagnetic simulations. Most of the cases, it's not necessary to feed this information back because the changes, the geometry changes are normally quite small and have not really influence on the electromagnetic part. And on the thermal part, it depends. If I create some extra thermal connections through to the extensions or shrinking of the system, maybe I have to feed the information back to the thermal simulations. But again, normally this is not really required, but could be done. Maybe as an information or something for what we're looking today, on the left side, I have single values as an input, constant values, or I have a function over time. On the right side, you see I have distribution. The temperature, the losses, the stress, they are localized. They are connected to a position, X, Y, Z position on my system. So that's distributed values. So that's the general workflow multiphysics simulations. What's is now the challenge? So the challenge was, or the challenge here is, I want to know how my component, could be this laser diode, could be a half bridge system, could be power electronics, that could be PCB, which includes the controller, for example, doesn't matter. I want to know how this works in an operation condition. I don't want to know what's the worst case. Yeah, that's also sometimes interesting. Or what's the standard, the steady state case. I'm more interested how this behaves in my system, how this behaves in my working conditions. So that's the challenge which we want to look today for the multiphysics system simulations. And I've put it up here, 3 questions. I didn't do the questions mark behind, but that's 3 topics which I want to go into today. First, different timescales. Okay, we'll see there's different timescales on how the physics react to changes. Then we have in the electromagnetic the problem or the issue that a lot of properties also depends on frequency. Yeah, or not only on the frequency, more on how fast current changing. If the current changes very fast, I get higher inductions. The induction behavior is different and so on. So I've also looked into this one. And the last point is what I want to do with the system. I can simulate it once, okay? But normally I want to do it for different scenarios. I have a lot of different scenarios. Or I want to keep it running parallel to the operation of my system. So that's the last point, is looking into, one word for this one is digital twin or real-time calculations to monitor your behavior. Okay, so let's start with timescale. What I mean with timescales. The electric conductivity or electromagnetic behaviors, we easily have some kilohertz, 10 kilohertz up to megahertz in the system of switching times. It doesn't have to be the sinus. It can be also the signal which is switching very fast. We have a very high frequency in the system. To really capture this one in simulations, you have to make very small time steps to capture these changes. Could be sinus, could be a change of 0 to 1, whatever. If I want to capture this correctly, I have to make very small time steps in the simulation because I have to get the point where the change is. On the other side, on a thermal simulation for the same system, in the range of microseconds, which corresponds to some kilohertz frequency, nothing happens in the temperature. Temperature has a high thermal capacitance, there's thermal conductivity. The whole system is a little bit slower and it depends more on the energy which you have to put in. And if you make it change very fast, the energy which you put in is not this much. Yeah, that's a different relation. So to see a warm up in the system, some relevant change of temperatures, you're more in the range of 100 milliseconds, seconds, maybe minutes, maybe hours, depending on your system. Why is this important? If I want now to simulate the electric behavior and the temperature behavior at the same time, I always have to take the time steps of the simulations of the system which reacts faster, which needs the smaller time steps. So in this case, a coupled electric thermal simulations have to make a lot of time steps, maybe in a microsecond range, but on the temperature side, nothing happens. It cost me time to simulate it, but the temperature is not changing. Maybe a little bit more drastical to see it is it if you compare electric properties and mechanical stress. I said before, we want to look into stress in the system. It gets warmed up, cooled down. Maybe the humidity change. That's something which we don't simulate in our system, but mainly the temperature and the stress. And that leads to failure. Yeah, it can somewhere break the system, it cracks. And if I make a product, I want to know what's the lifetime of my system. Yeah. Typical values, I don't want to have that more than 15% of my devices fails after 10 years. Okay, there's a lot of different reasons why it can fail, but one of them could be stress, thermal stress, mechanical stress. The contacts get broken or something get disconnected, and then it fails. And then we are here in years. So on the left side, microseconds. On the right side, we're talking about years. So I can't use a simulation at the same time to see, okay, what's happening if I use it at 10 years. So that's one of the challenge. When we talk about simulation or simulation approach, you might hear often something called field coupling, terminal coupling, system simulations. Field coupling, that's what you see on the left side, is something where we have 3D geometries, where I get these nice colored plots, where I get local distribution of the system, normally very high accuracy of the system, but that takes to simulate. On the right side, you have terminals, so you have some input, some output, and a function between which connects the input signal to that what should come out. Simulates very fast, yeah, microseconds, whatever, but I don't get the localized results. I know only if I put this input, I get the maximum temperature of the system out, for example, the mean temperature, the temperature on one point, which I might be interested. Maybe I should explain this a little bit more if you're not familiar with the whole simulation range or what we talk about simulation. So if I talk about field simulation, I'm talking about a system where I discretize my problem. So a typical code, I create a mesh that could be using finite element methods, can be FDTD method, the differential time domain method. There are a lot of different methods there. I have normally the physics described by partial differential equations. Yeah, an example for electromagnetic, that would be the Maxwell equation, which I want to solve. I can't solve these equations analytically on complex geometries. On very simple geometries, on a line, a straight line, whatever, I can do this, but not for complex geometries. So that's why I have to discretize the problem, solve the relevant equations, which I'm looking into in each of these elements by some approximations and numerical methods. But you can imagine if you have such a mesh for each element, you have to do this. There's some high computation power. Yeah? So the good thing is I get high local fields. I understand the system. I need heavy computation time, means power, time. And I can use this normally for design validation, where I'm really interested what's happening there and there, what's happening if I do some changes. On the system simulation side, I'm using normally ordinary differential equations, yeah, or other functions which described some input to an output. That can have already quite detailed information in it. It's not distributed, it's not localized fields or something which I can get out. I can get several outputs, minimum, maximum on several points. I'm even possible to get something like out discolored temperature maps or power loss maps, if I want, if I put some mathematical methods in it, but the information behind the system is much less. I can't look into it. I can't look what's happening on this point afterwards. Everything is defined before, which outputs I want to get. It's something which I use for dynamic simulations. That's what I said before. I want to know what's happening over the whole application, what's happening over the whole operation time. So that's why I'm using system simulations. And what you might know from electronic engineering, concentrated elements, lumped elements, is also another name for this one. I have a resistor. I can describe this resistor by the voltage on these two ends of the resistor and the current flowing through. And if I know the resistor, the R value, I get the other information which is missing, the voltage or the current. I can calculate this one. In general, that's not heavy for calculations. That can be done very, very fast. But I don't get the information on how's the current distribution in my resistor. Is there at the input maybe higher current density because of the contact, and then the current density goes down, or is there locally somewhere a problem with very thin conductivity or conductivity area, high losses? This information is not. It's one part. It's described by the R value, and yeah, I can use this for circuit simulations. Another thing is this one is not connecting to the induction which is next to it. There's no information on where is it positioned. If you try to make then the circuit, you can connect the resistance with an inductor, but they don't know how close to each other. If I have two inductors, that's a problem because they can interact over the electric and magnetic fields. If I make only concentrate elements, they don't know where they are. And now about the coupling. Yeah, so we want to couple different physics. We want to make coupled analyzers. So that means we can do field simulations, which you see here on the left side. I mean, the strength is you have the high accuracy. You really have the geometry. You can see what's locally happening. You can couple the electric degree of freedom with the thermal degree of freedom. So you can go into the detail. You can describe your physics very accurate. And you can get a lot of information, even nonlinear materials and so on. Yeah. The cons is if I do this one, it takes time. First, I need the time to prepare this one. I have to set up the simulations, then the simulations runs, and then I have to make the post-processing to get my plots and to get the information out of this one. The other point is, which is important, I need already a geometry. I have to know the materials. Without this knowledge, I can't do any field simulations. On the side of system simulations or multiphysics, in regard to multiphysics, it's a simplified problem. I can include interactions between thermal and electromagnetic, for example, or thermal and stress by connecting the average temperature, the temperature on some point, and I know my system, and then I can calculate the temperatures around it, and so on. It's good for dynamic simulation. It's much faster than the full field simulations. Yeah. Again, I have a limited resolution. If I would make the same number of pins here, then I have elements here, I would get the same resolution, but no one is doing this. I don't think it would even work. In general, that's the idea. And I can get the local hotspots. Where I get this system simulation models, there are libraries, there are tools which provide you with models. But what I can do if I don't have a library model, I want to use my 3D model, which I have maybe done already for field simulations. Now for dynamic system simulations, that's what I want to show them later. And lumped elements, I think I explained it already. It's very basic. I can use resistors, inductions, capacitance, voltage sources, and can calculate if I have this input voltage, this input source, what's the resistors, losses, and so on. So, but I lost the information about any connection between the tools and so on. So again, coupled analyzers, I have field coupling. Unidirectional, bidirectional means I can take the thermal and electromagnetic simulations step by step, or I have to solve it at the same time. That depends on how fast these two reacts. And I have the system simulations or terminal coupling on the right side. I want now to focus on this here on the right side, system simulations. That's also the topic of this presentation. So we want to do coupled analyzers or multiphysics simulations. We want to use terminal coupling, and we want to use system simulation because we want to describe how a system behaves over a long time or over the operation time. So the system simulation, I can set it up with concentrate models. As you have seen before, I can use a resistor, I can use an inductor, I can use the same in the thermal part. I can use the thermal conductivity, similar to a resistor or electrical resistivity, to make a lumped element model of my thermal behavior. I can do the same for fluent system where I have gas as a flow going through. So I can describe this by concentrate models. It's generally based on mathematical models, physical equations, as we have seen before, Ohm laws I can use for this one, for example, and so on. Or also more complex equations. I could use the temperature-dependent conductivity together with the size of the resistor, and then I can get the voltage dependent also on the temperature and the current which I have, for example. I can use libraries. There are standard libraries. There are a lot of system libraries available, free, open source, but also someone which you have to pay for it. It is easy to exchange between tools, between companies, between departments, and it calculates very fast, but have in general a lower accuracy because a standard resistor don't describe my specific resistor. So that's what I have to think about. Co-simulations, that would be I make for the part which I don't know a circuit or system simulations, and for the part which I know, the PCB for example, that's something which I have created, I know the geometry, I make field simulations. So I have still the high accuracy of the field simulations of the part where I do the field simulations, use it together with lumped elements, circuit elements to combine my whole system. But that's not really saving time in simulation because the field simulations have still to be done for each time step, so still long simulation time. And the third part is reduced order models or also surrogate models named. I have used a reduced order model description for this one, which are mathematical functions, ordinary differential equations, different methods to reduce the complexity, but keep still a higher resolution than for the concentrated elements. The disadvantage is this needs some effort to create these reduced order models. And there are different methods available. So what I mean with reduced order model or surrogate model, there are, as I said, there's a lot of different methods how you can do it. It's mainly based on mathematical methods or on machine learning systems. So you simulate different cases, case A, B, C, D, and you see what you have put in and what's the outcome, and you try to make a connection between these two by mathematical equations, by data table, by reducing the numbers of degree of freedom, like modes which you're using. And then you have this reduced order model. And this reduced order model is then in general something like a black box. You don't really know. There's not the physical equations more anymore. It's more a description. But what it means on the right side, this figure, is if I want to use these reduced order models, at the beginning, I have a higher investment because I have to make first a simulation for the scenario A, B, C, D. Because I need the scenarios A, C, B, D to create this mathematical model, which runs afterwards much faster. So if I want to make only one simulations for one scenario, maybe the full model simulations is faster. But if I say, okay, I don't change the geometry anymore, I only want to know regarding on the input parameter. I want to run with higher currents. I want to run it longer. I want to make higher switching times. Then it's useful to have this reduced order model, surrogate model, which cost me at the beginning some time to create it. But when it's created, my simulations runs faster. That should be shown here on this graph. So if I have a lot of time steps, or I want to run several variations of input parameters, at some point, the reduced order model, the system simulation is faster than running the full model. Yeah? But at the beginning, I have to invest some time. When we're talking about the reduced order model, we have to think about classification. So I think that's the biggest challenge to create reduced order models currently, is I have to know first what I'm describing. I can't use all the methods on the same problem. I have to understand the problem. Is my problem a linear problem? Can be the material properties seen as a linear? Can be the connections be seen as linear? Or is it nonlinear? Yeah, I have the thermal conductivity change with temperature, highly nonlinear. Then I'm here on this part. If I'm linear, I'm this part. The next question is, can I see my problem as a static problem or as a transient problem? Static means if I put a certain input, power, I have the cooling, and then I get the temperature out. It doesn't depend what's happening before. But if this behavior depends on before, if it was it cooler, was it hotter before, and then apply the power and so on, then I have a transient problem. And then you get this here kind of complex matrix where you have scalar values, field values, linear, nonlinear, static, transient. So that could be something, scalar values, could be a function, could be a table, whatever. Field results is always something which is slightly is connected to the geometry, to the location, and you can put it in each of these fields, and then you have different techniques. In this webinar, I will not go in all the techniques or discuss the methods. It's not techniques, the methods to reduce order models, but you see specific on your problem, there are different methods to create such a reduced order model, and that's done already for a long time. What I would say which is slightly new in this graph is that we have machine learning and AI here in the middle. And that's also a big potential because that can also help me to understand, is it a linear problem, non-linear problem, is it a transient problem by the creation of the model. So complex matrix. I want to explain this one, or I want to show you an example with the laser diode, which we have seen already at the beginning on the multiphysics workflow. As I said, that was a project which we did together for seeing how we can handle this one or how we can do this one, which reduced order model is suitable for the problem. Maybe there's several reduced order methods which can be applied, and we compared this one. So the challenge was the time resolutions, because we didn't want to know what's a constant current. We wanted to know what's happening over time for different input parameters. Temperature is changing, current is changing, the environment parameters are changing. So we wanted to do a system simulation. And we want to know, has it influence on the lifetime of the system? Well, the question was, the system is built for 50 amps maximum peak for this time. Can I run it with 60 amps? Is it broken in one day, or is the lifetime only reduced by 10% or something? Yeah, so that was the idea, and also to create a digital twin model out of this one to run these different scenarios. So one part is the electromagnetic properties, which we want to extract. So you could imagine from the geometry on the left side, you take one of the current paths and you can extract the resistance of the part. You can make it in smaller steps, that you take these bond wires here as one part, you take the weir as one part. So you get this equivalent circuit of resistance, and you can simulate this for different frequencies. So as we expected, the resistance goes up with higher frequencies because we have the skin effect and so on. So that's frequency dependent. Can also take the same geometry. We can analyze the inductance, for example. We have there always the self-induction and mutual inductions, which we can calculate. If we know the inductions, we can know also the coupling coefficient. So how these two bond wires, for example, coupling, or how this bond wire is coupling with this bond wires, which maybe if there is some current flowing, which is switched or sinus, then we get also some current in here because it's induction. So we get the inductions, we can extract the capacitance, and then we create a model. Maybe many of you know B-Spice as a model, or H-Spice. Some of you may know Touchstone. So that's models of the electromagnetic behavior of your component. Sometimes you can get it from your part support, or from your company which made the parts as a model which you can put in your circuit simulation. But we cannot extract it from the field simulations. So if you look into this in more complex, you have the different paths. I have divided in several resistance. I've done this also for the inductions. And finally, I get out a block. It looks like this one. And I can use this then for system simulations. In the block, you get the information on the resistance, inductions, of the coupling, and so on. It's an electromagnetic problem. But we still have the issue with the temperature. So if I look how the resistance increases with temperatures, I run here a little bit high with more than 200 degrees Celsius. It's maybe too much. But anyway, even if I'm here between 0 degrees Celsius, 100 degrees Celsius, I see a significant increase of resistance. And the important point is higher resistance mean also immediately higher losses. Higher losses means it's getting warmer. So it could be a runaway effect, if I don't cool enough the system. So I have to put also in this temperature behavior into this one. Then I made a reduced order model, surrogate model for the temperature behavior. That can be done similar to the electromagnetic simulations. I applied losses, power losses to the different parts and simulate the temperature which is created. And then I can extract as this matrix of these several field simulations. I have to do these field simulations for different scenarios. From these scenarios, I can learn and can create a reduced order model. Maybe you've heard of LTI model, linear time invariant models. There's something which is called MOP, which is a meta model of optimum prognosis. There are design of experiments, tables, and so on. So what I'm doing is field simulations for different input scenarios. They must be chosen in a wise way so that I get the information which I want. But normally software can help you to this one, which method is the most useful. If you have seen the matrix before, there are methods which are explicit for extracting thermal behaviors and for is it linear, is it non-linear behavior, and so on. So I can again create such a surrogate reduced order model. So I run all these simulations here. In this case, it was not too many. It was 9 simulations. But if I have more inputs, I get more localized, and maybe have several more simulations. And again, I get out a block. And now I have the information of heat generation input values, and I get out the temperature of the system. How does such a system, multi-physics system simulations look like? So we take our laser diode system, which we had before. I have here our input parameter, that's the current test scenario, which you see here. That's in my circuit, the current sources here. The current goes into, into the electromagnetic part. In the electromagnetic part. And from the electromagnetic part, I can measure the losses. And I use these losses on the conducting path as an input on my thermal model. I have additional losses in the lasers. As I said at the beginning, I don't want to model the laser, the semiconductor part in specific. There I took the data table. There is some information. If I put this current on this laser part, I get these losses. Also, I measure the losses here. It's not really necessary to make all this measurement equipment in here. There's also other ways to make it more nice to view, but it should show that there is a lot of measurement instruments. And finally, I have these 2 reduced order models on left and right side connected with my circuit, and I run the simulations. And that's the output of the temperature. And then I compared this one with a full field simulation, and we can see that we have here in general the same behavior. It's not exactly the same. Yeah, that's not to expect, because the reduced order models have less information, less details, but the general behavior is quite similar. And also if I look to the temperatures, for here a little bit more than 28, here a little bit more than 28, that fits quite well. What's the difference? The system simulation runs in less than a second. I've written here a few seconds, depending on the complexity, but this simple model was running in less than a second. The field simulation took several hours because there's a very fine mesh. I have a lot of degree of freedom, so I need a lot of time. I want to make now a short introduction or a short turn to the current distribution, which is in the power electronics also very important. I think everyone of you knows if I go up with the frequency, the current path can change significantly. In this example, I have here a track. I have a PCB substrate and a ground layer below. If I'm at very low frequency, you see here the vias, and the current which is introduced in this track here will go through the vias and in the ground plane direct way to the other via and go up here again. So that's the current path. If I go up with the frequency, we will see that the current is now not flowing anymore the shortest way or the shortest connection between the vias. So now, it's running where I get the lowest inductions. So the current tries to flow under the track. So that's what we see here in the orange part. So it takes a larger way, which changes the resistance and so on. But that's for the energy, for the total energy, more convenient that the current flows under the tracks. And if I'm going up to higher frequency, then I can see even the effect that it's the current flowing only on the surfaces. The distribution change a little bit. And this has the influence that also the losses, where the losses appears, changes. And if I do a multiphysics electric thermal simulations, I have to know where the loss is happening. At 100 hertz, there's more losses here. At 100 kilohertz, the losses are very high here around this cutout. So I have to get this information. So we looked into a power electronic system. That's a half-bridge system, but could be also a busbar system, battery connector, inverters. Yeah, you can, everywhere where you have the power electronics, you can look into this. So the losses of the device is not distributed evenly. So I have hotspots, which can influence the lifetime, the efficiency, and so on. And I have to analyze these phenomena. I have to see under which operating conditions where are the losses. And that's where I'm using a thermoelectric system description of the problem. So here again, a geometry, as I said, a half-bridge system, inverter system. We have the capacitance, we have the semiconductor parts, the MOSFETs in our systems. And the problem is we want to know how's the temperature distribution, how's the current distribution, because also the temperature distribution can influence how much current flowing of each of these semiconductors. This could change. If I do a full coupled electric thermal simulations, this is very time consuming. You see here some time steps. I made a transient simulations that run on a larger computer, not huge, but larger computer, several days. But afterwards, I got this nice picture. I could see for each time step where the current distribution is. I can see which via have very high currents and how I can optimize it. The idea is now to go to the system simulation. I have the same problem as before. I want to couple electric thermal, maybe structural, and I want to connect them. So, you know, standard electric circuit simulation here on the left side. So temperature is not really included in this one. There's no information on the temperature. We don't know the parasitic losses of these black lines here, which is the PCB, that's the bus bars, whatever. They're not included. We don't know the local currents, or the losses are not considered. If I make a reduced order model of my conducting structure, bus bars, PCB, whatever, I get the parasitic losses. And can they extract them and can put it into my circuit? So in this case, I also know, okay, there is losses in the conducting paths which connecting the components. Here are only the components. here the conducting parts plus the components. And then I can make the parts, the semiconductors. There are models which also include some temperature information and how much losses they created. So I get now also the temperature behavior into the model. And even I could take the thermal conductivity, as we have seen before, into this system simulations. But what's still missing in this part is the local currents and losses are not considered. And that's something which we looked in another project, how we can also include information on the local distribution. And what we have done is, instead of using a single input and a single output, we describe the current distribution, which we have done first field simulations with different input parameter. Out of the field simulations, we get then something like modes. So we can describe the current distribution by a number of 10, 20 modes, which are important. These modes can be stacked together, for example. We can create out of a single or of a small number of modes the complex current distribution. We have seen already the matrix before, which we have for the state space model, for the resistance, inductions, and so on. We can put in the temperature dependency of the tracks, and we have the thermal model. And with such a setup, as I said, we have different modes. The modes consist of the different input parameter. They describe the current distribution. We have the temperature dependency. We have the thermal ROM. We could recreate the field simulations with a system simulations, again, by reducing the simulations time by a significant number, 100 times faster, 500 times faster, depending on the problem and how detailed you looked into it. But we really could describe the voltage comparison between these two systems. So that's something which you can do with reduced order model, with surrogate models, when you create it to look into details, if you want to get a more detailed model than a lumped element. Finally, what's digital twin? So now with this reduced order models, which simulates very fast, which can calculate very fast the results, we have the basic elements for doing digital twins. So that could be the signal input, can be known before, can be measured. I have my electromagnetic model, I get the losses, I have my thermal model and my mechanical model. I haven't mentioned it before, the thermal model, but it's again like the mechanical model. It's again like the electromagnetic thermal model. You can create a reduced order model which gives you information on what's the maximum stress, where's the maximum stress, and so on. So I have the models, the simulating fast, less than seconds for each time step. It's microseconds, so nearly in real time, I would say, or in real time, depending on the problem. You can measure your input parameter, thermal loads. You can measure mechanical loads. Is it shaking? Is it not shaking? Was it fallen down? You know your environment. Is it hot? Where is it built in? So you have this simulation path. And now you can use the output from the simulation, the temperature, to manipulate your thermal input parameters. Maybe you want to have more cooling, or you decided to reduce the power, less power, because you don't have enough cooling in the moment, because the thermal loads is too high, or the boundary conditions is not well. Or for the mechanical stress, you see there's a lot of mechanical stress, warm, cold, or there's a lot of mechanical loads. You want to increase the lifetime, so you reduce again the power, so that the warm, cold, the stress is not too much. You increase the cooling, or you decide, okay, we have to make a maintenance a little bit earlier than planned because this part was really heavy used. So that's part of the digital twin. And yeah, the idea is from the reduced order model, from the system simulations where I started, you have already these parts. Now you have to include it only in a system which then can also interact with the controller, with the measurement system. Yes, and from here, I'm coming to my summary and outlook. Yeah, the idea why I'm using system simulations for electric, thermal, mechanical simulations, I wanted to explain. So what's the advantage of system simulations compared to field simulations? And what you get more with system simulations than when you use standard lamped elements or concentrate elements. I wanted to show that model order reduction is something, there's a lot of tools available, there's a lot of methods available, but depending on your physics, on what you want to describe, is it linear, static, nonlinear, transient, you have to choose the right tool. The ROM accuracy depends on this reduced order model accuracy depends on which method you use, how much effort you put in, for sure. They can be very accurate. It doesn't mean that reduced order models are not as accurate as field simulations. Field simulations have more information. Yeah. We can use the reduced order system simulation for transient simulation over a long time. And it's important to know where you have your local heat. So that's why system simulations combined with field results could be very important, that you can optimize the cooling system and so on. And ROMs, reduced order models, are an important tool for creating digital twins. That was the last 2 slides which I've shown. It's the basics, in my opinion, for creating digital twins.